In this video, we're going to take a look at transformations. Transformations are ways in which we can modify the graph of a relation or transform it. So we're going to look at 10 of them, 5 that affect the x variable and 5 that affect the y variable, or whatever the two variables happen to be. So x and y are common ones. Why are we interested in this? Well, transformations they aid in graphing a relation. They can make graphing a relation quick if the relation is similar to another relation. And we're going to talk about that in today's video. And then they also could help in application. So let's say you ran a business and you kept track of your sales data and you had the previous year's sales data. So say you kept weekly sales data and you've graphed all of it for the whole year, the previous year. And let's say you were interested in what would that look like if sales increased 30% or decreased 40%, or what if you wanted sales to go up $1,000 every month? I wanted to see what that looked like. So these are all things you could handle with transformations. So let's take a look. Just a quick reminder that for us, we typically use y and x for our two variables. X would be the independent variable and y would be the dependent variable. So variable here. Now, if we've determined that y is a function of x, then we can, instead of using y, we can use f of x in its place, or g of x, or h of x, or whatever name you want to give it. So remember, f is the name, and what's in parentheses is what y is a function of. So is it a function of x? And there'd be an x there. Is it a function of time? You'd put a t or something there. So it lets you know what you're a function of. So again, we're going to look at 10 transformations, 5 of which change the y variable, and then 5 which affect or change the x variable. In no particular order, we're going to start with the 5 that affect the dependent variable, or y. And the first one we're going to look at is what's called a vertical shift. So if you draw your xy plane in the customary way, then the y-axis goes up and down. So if your whole relation moves up or down, then we call that a vertical shift. And the way we're going to define that is we're going to let f of x be a parent function. Now, what do we mean by a parent function? We mean that f is some function we're familiar with, and we know its shape and we know its properties. So it's something we're familiar with, and starting with that, we're going to create a new function. So since we're creating something from f, we call that a parent function. So we're going to let f be a parent function. Then if our new function g is function f plus c, then the graph of g is the graph of f shifted up c units if c is positive, and shifted down c units if c is negative. So c is a constant, c is some real number, and if c is positive, then when you add a positive number to f, you get a new function, we'll call it g, and basically all it is the y values of f have had a number added to them. So you take all the y values of f and you add whatever c is to them, and then replot them, which would just shift the whole graph up. Now x would stay the same. We're not doing anything to x, we're just adding c to y. But if c is negative, then you're adding a negative number, which would effectively decrease the value of y, so the whole relation would move down c units, so the whole function would move down. So for example, let's say we have this parabola right here. That's f. So f is right here, and we want to graph f minus 2. So we want to shift the whole thing down 2 units. So for example, the vertex, which is at 1, 2, so it's at -2, -1, well, that coordinate is now going to shift down 2, so it's going to be at -2, -3. So it's going to be at -2, -3. Or this point here, which is at 0, 3, or, I'm estimating, but it looks to be about 0, 3. We're shifting it down 2, so it's going to be at 0, 1. And then this point over here, it's a parabola, so we have some symmetry. At -4, 3 is going to be at -4, 1. But it's the same shape. Everything's just been shifted downward. So the graph would be the exact same shape, so it still would be a parabola. It's just been shifted down too. So we're just gonna subtract 2 from all y values. So this is y, and this is -2. So subtract 2 from all y values and replot it. It just shifts it down 2 units. So that's just a shift downward of 2 units. If it was +2, we would just add 2 to all the y values and shift it up 2. Well, next up, what if we want to stretch it or compress it vertically? So we don't want to move the whole thing up or down. We actually want to adjust the shape a little bit. We actually want to stretch or compress. So again, we're going to let f of x be a parent function. Then g, which we're going to define as c times f of x. So c is just a constant. Is a function whose graph is the graph of f stretched vertically if c is bigger than 1 and compressed, or squished if you like that better, compressed vertically if c is between 0 and 1. So as you know, multiplying a number by something bigger than 1 increases its magnitude. So if you take the number 6 and you multiply it by 3, that's 18. So 6 increased in magnitude 18. But if you take a number like 6 and multiply it by a half, it decreases its magnitude. So 6 times a half would be 3. So same idea here. We're just going to take, remember, y is f of x. So we're just going to take y times 2. So we're just going to multiply all y values by 2. So we're going to stretch it vertically. The magnitude of all the y values is going to increase by a factor of 2. So for example, this vertex here, which is at 1, -4, 1, -4, so go right 1, 1, 2, 3, 4. If I multiply by 2, it's going to be at 1, -8. It's going to be at 1, -8. So if I want to fit that on the same scale, I'm going to need my axis to go a little further down. So we go 1, 1, 2, 3, 4, 5, 6, 7, 8. So at 1, -8. And then let's get a couple more points. Let's do this point here. So it'll be 1, 2, 3, 1, 2. So I do 3, -2, but I'm multiplying y by -2, so it's going to be 3, -4. And then let's come over here, do -1, -2. Be a -1, -4. So now it's got the same shape though. It's still going to have this V shape. So draw in our V shape here. But notice it did stretch it vertically. So it brought the sides in and made it a little bit more narrow. So if I were to put the parent function on here, so write 1, 1, 2, 3, 4. So here's the parent function. I'll do it in red. Notice the parent function was a little wider. And then after we stretched it vertically, it became a little bit more narrow. So the blue one is our new function, 2 times f, and the red dotted one is the original parent function. Now, if we'd have multiplied by a number between 0 and 1, that would have increased, it would have decreased the magnitude. It would have made the y values smaller, closer to 0. So it would have got wider. So that's 4 transformations. Let's go back and look. That'd be 4. So I can shift it up. That's 1 transformation. I can shift down. That's 2. I can stretch vertically. That's 3. And I can compress vertically. That's 4. There's one more that changes, that we're going to look at, that changes the y values. And that's a reflection about the horizontal axis. So the horizontal axis for us is usually the x-axis. So again, we're going to let f be a parent function. Then the graph of g, which we're going to define as -1 times f of x. So -1 times f of x is the graph of f reflected over the horizontal axis, which is usually the x-axis for us. So basically, remember y, so y is f of x. So this is y times -1. So we're just going to multiply all y values by -1. So just let's pick up a few points here. So like I've got -3, 1. So this is my parent function. So this is a square root function. This is our parent function. So it's a function we're familiar with and know the shape of. Now if I multiply that y value by -1, it goes to -3, -1. And let's say I pick this one here, which is -2, 2. If I multiply that y value by -1, it's -2, -2. Or if I do this one here, 1, 3. If I multiply that by -1, I get 1, -3. So it just flips the entire function, it's a function in this case, the entire relation over the x-axis. Same exact shape, no squishing, no stretching, just flips it over the horizontal axis. So if I put the parent function back on here, it was right here, but that got flipped. So imagine folding it over the x-axis. It would end up where the blue one is. That's our new function. So if you ever want your entire relation to flip over the x-axis, you just multiply all the y values by -1. So that's 5 transformations that affect the y variable or dependent variable. So now let's go look at 5 that affect the x variable. Now what I want you to notice here is physically what's happening to the function's definition. And notice that x is replaced each time. So I'll show you what I mean. So earlier we shifted the whole relation up and down. Now what if you want to shift it left or right along the horizontal axis? So a horizontal shift, let's start with a parent function. So let f be a parent function. then the graph of G which we're going to define as f of x plus h is a constant, is the graph of f shifted left if h is positive, and shifted right if h is negative. So if you have x plus a number in the parentheses, you're actually shifting left. If you have x minus a number, you're actually shifting right. Now, the explanation for why it works that way is a little lengthy, so I'm not going to include it in the video. This video is going to be long as it is. But in class, we'll talk about why it seems backwards. See if we can't convince ourselves that it's going to work a little differently when x is involved. So I've got another parabola here for us. So here's our parabola. This is f right here. So this is the graph of f. And we want to graph y equals f of x minus 4. So what I want you to notice is the original parent function is a function of x. But our new function is a function of x minus 4. So x was replaced with x minus 4. So everywhere that there was an x in the equation is now replaced with an x minus 4. That's different than the 5 transformations that affected y. If you go back and look, y was just f of x. So I had f of x times negative 1. Or I had f of x times 2. Or I had f of x minus 2. So f of x still showed up in our new function. But for a horizontal shift, and as you'll see, the remaining ones, f of x doesn't show up. It's f of something else, in this case, x minus 4. Well, since it's x minus 4, h is negative, we're shifting to the right. So we're going to add 4 to all x values. So for example, this vertex, which is at negative 2, 3, if I add 4 to that x value, I end up at 2, 3. Or this coordinate here, which is at negative 4, negative 1, if I add 4 to it, I'm at 0, negative 1. And this coordinate here, which is 0, negative 1, if I add 4, I'm at 4, negative 1. But it's the same shape. I am just shifting the entire thing to the left and to the right, in this case to the right. Same shape, so the exact same parabola, just pick it up and move it over right 4. But notice it was x minus 4, but I don't actually subtract anything. I add 4 to the x values. So that's 2 transformations right there, a shift left and a shift right. There's 2, so there's 3 more. I told you there's 5 for each. So what about a horizontal stretch or compression? Well, again, let's start with the parent function. So we're going to let f be that parent function. Then the graph of g, which we're going to define as f times, or not f times, I'm sorry, f of cx. So x has been replaced with cx. C is a constant. Is the graph of f compressed horizontally if c is bigger than 1 and stretched horizontally if c is between 0 and 1. So let's see what we got here. So here's a parent function. I've got this function right here. We're calling it f. That's our parent function. And then I'm going to take f, and instead of x, I'm going to replace it with 1/2 x. 1/2 x. Well, 1/2 is between 0 and 1. So this is gonna stretch it horizontally. This is gonna stretch it horizontally. So it looks like I take 1/2 times x, but what I'm actually gonna do is divide x by 1/2. Well, dividing by 1/2 is multiplication by 2. That's why it's going to stretch it horizontally. And again, in class, I'll show you why it works that way. Why it looks like you just take x times 1/2 according to the arithmetic here, but you actually take x and divide by 1/2. So let's see what happens here. So we're going to go 1, 2, 3 to the left, down 1. So this is -3, -1. And if I divide the x values by 1/2, which is multiplication by 2, that would end up at -6, -1. So if I extend my axis here, and then let's see, this coordinate here, if I take x and divide by 1/2, I get -4. And this coordinate here, we're just going to end up at 2, -1. And then this coordinate here, it's going to end up at 4, 3. And then I connect them in the same way. So the whole graph got stretched horizontally. It's as if you grabbed the left and right side and pulled it. It got stretched horizontally. Now, if this number would have been bigger than 1, it would have squished it or compressed it horizontally. Because if that number was bigger than 1, let's say we had f of 4x, now you're dividing x by 4. Well, dividing by 4 decreases its magnitude. So there's 2 more transformations. There's compress horizontally and stretch horizontally. So now we've got one left. We've done 4 that change the x values. We got one more that changes the x values. What if you want to flip it over the vertical axis? That's only fair, right? We flipped it over the horizontal axis earlier. What if you want to flip it over the vertical axis, or y-axis is what we typically would call that. So we're going to let f of x be a parent function. Then the graph of g, our new function, which we're going to define as f of -x, so we replace x with -1, is the graph of f reflected over the vertical axis. So notice, instead of f of x, it's f of -x. So once again, x has been replaced by something, in this case, -x. Well, just like before, we have a number times x. So we're going to handle it the same way. We're going to divide all x values by -1. So let's try it. So let's say this is our parent function f. That coordinate is -2, -1. But if I multiply or divide the x value by -1, it's at 2, -1. And this one right here, which is at 0, 3, if I divide x by -1, I get 0, 3 again. And this one here, which is at -4, 3, if I divide that x value by -1, I'm at 4, 3. So if I graph that, same shape as the parent function, parabola, but it's been flipped over the y-axis, vertical axis. So that's all 10 transformations. Shift up, shift down. stretch vertically, compress vertically, flip over the horizontal axis. Those 5 change the y values. Shift left, shift right, stretch and compress horizontally, and flip over the vertical axis. Those change the x values for a total of 10. So, a little shortcut, a little way to kind of keep these straight, because 10 sounds like a lot, but it's actually not that bad if you kind of look for some patterns and clump it all together. So if the function is given explicitly in terms of the independent variable, then the transformations can be determined quickly. So if your parent function y is given exclusively as a function of x, so you got y equals and then a bunch of stuff with x, then you can kind of clump these together. Y equals f of x plus or minus c, y equals c times f of x, and y equals negative f of x. Those are your 5. So if c is positive or negative, it's a shift up or down. If c is bigger than 1 or between 0 and 1, it's a stretch or compress, and then flip over the horizontal axis. That's 5 right there. And then for these, you just do exactly what the arithmetic says. So for example, you take y times negative 1, because that's what it says to do. It says take the y values of f times negative 1. This one says take the y values of f times c. This one says take the y values of f plus c, or minus c if it's a negative number. You just do exactly what the arithmetic says. Whereas these, so left, right, shift, compress or stretch horizontally. Notice it's f of some new variable, f of x plus c, or a new expression, I should say. So f of x plus c, or f of cx, or f of negative x. So it's f of a different expression than what the parent function had. These, again, in class we'll talk about why it works this way, but you do the inverse arithmetic. Indicated to the x values of f's coordinates. So, for example, right here it says, it looks like you take x times negative 1. Well, instead of multiplying by negative 1, you're going to divide by negative 1. And I know you're thinking that's the same thing, but it's easier to remember it this way because it works for all of these. So, for example, on this one, it says take x times c. Well, no, you're going to divide by c. And depending on what c is, that'll stretch or compress. And this one here, if c is positive, it looks like you take x plus c. Well, no, you do the inverse. You do x minus c. So you just do the inverse arithmetic that's indicated to the x values of the parent function. So really, there's only 2 groups here. You either do exactly what the arithmetic says, or you do the inverse arithmetic to x. So it's a little easier to remember when you get the hang of it and think of it this way rather than 10 transformations. So let's try it. I know we've been talking about f's and g's and some constants. Let's actually do some with some specific functions. So for example, let's say we wanted to graph g is negative quantity x minus 2 squared plus 3. Now, we could do this the old-fashioned way and just make a t-chart and get a whole bunch of points. And then once we get the pattern, we could finish drawing it. Of course, that's an option, but that's very slow, especially if you don't recognize the function. Where what we're saying now is you may recognize the function as just a more complicated version of something you already know. So this has an x squared, and then that's it. Just the rest of it's just some arithmetic. We got an x squared. There's no square roots. There's no absolute value. There's nothing else. It's just got an x squared. That's very similar to a function we're familiar with, which is y equals x squared, the squaring function. That's just a parabola whose vertex is at the origin, opening upward. So we're familiar with that graph, and we could graph it very quickly. Well, this is just a more complicated version of that. So using transformations, I can pretty quickly get the graph of this. Now, it's not going to seem quick because I'm going to walk you through how these transformations work, and we're going to write a lot down. But if you were doing this on your own, it would go a lot quicker. But as you do it for me, for homework and for assessments, yeah, you're going to have to write some stuff down so I have an idea of whether you understand the transformations or not. So the first thing we would do is we would start with the parent function. I'm going to call it y1. I'm going to call it y1. We're going to make a quick t-chart, and I'm going to ask that you guys do 5 points on the parent function. 5, not less than 5, not more than 5, just 5. You can do more if you want, I guess, but I think you'll agree that 5 is plenty. Now, those 5 points need to be 5 points that if you plotted them, you would know exactly how to draw the rest of the graph. So since this is a parabola whose vertex is 0, or located at 0, I'm gonna make sure that 0 is one of my x values. Now, it's a parabola, so it has some symmetry. So I'm going to go a little bit to the left and a little bit to the right. And I think these 5 points, if I were to plot those, I would know exactly how to graph that parabola. Now, using those 5 points, I'm going to apply my transformations. So let's look and see what my transformations are. So one transformation right here is I have a -1 times a big expression. So that is, we're going to multiply y by -1. And then I've got another expression right here. And another expression right here where I have an x minus 2 in place of x. So that's another transformation. And then I also have this transformation right here with this +3, which is a third transformation. So there are 3 transformations here. I'm going to multiply something by -1. I've got an x minus 2 that's replaced x, and I have this +3 tacked onto the end. So let's see how the transformations come in and help us. Well, starting with this parent function, I could apply a horizontal shift and replace x with x minus 2. So if I take the x out and replace it with x minus 2, I shift that whole parabola to the right 2 units. Well, now I get this new function, y equals x minus 2 quantity squared. So if I take that new function and I multiply it by -1, I flip this function over the x-axis. Well, now I've got this third function, this other brand new function where I've got -x minus 2 quantity squared. If I take that whole function and I add 3 to it, I get yet a brand new function, which is g. It's our final one. So to get g, I'm taking this third function and I'm going to add 3 to it. So basically, I'm going to build the more complicated function using my transformations. So let's see how that would work. Here are the 5 points I'm going to work with. This first transformation, I replaced x with x minus 2. So I do the inverse arithmetic. So I'm going to add 2 to x. I'm going to add 2 to x. So if I add 2 to all these x values, I get 0, 1, 2, 3, 4. I didn't do anything to the y values, so the y values stay put. I just add 2 to all the x values. Notice I don't plug anything into the function, but if I did, it would work out. If I plug 0 in, I do get 4. If I plug 1 in, I do get 1. But that's not that's not what I want to do. That's slower than just knowing the transformation and applying it once you get the hang of this. Now I've got these 5 points on this function, and I want to multiply that whole function by -1. So look, y is this, that is y. So there it is again, there's y times -1. We have a transformation that says if you take all the y values times -1, it flips it over the horizontal axis. So that's what we're going to do. So I'm going to take these y values times -1. So if I multiply them all by -1, I get these y values. But I don't touch x. I didn't do anything to x. The transformation just says to take y times -1. So I get these 5 y values and these 5 x values that go with them. So basically all I'm doing is taking these 5 points that we know define the shape that we want, and I'm just applying transformations over and over again until I get points on my final graph. Well, that brings us to our last t-chart, where I take this, notice that's y, so y is this expression, it's right here. So I take y plus 3, so I'm just going to add 3 to all these y values, but the transformation doesn't say anything about touching the x, so we're not going to touch x. And now I have 5 points on G's graph. So 0, -1, 1, 2, 2, 3, 3, 2, and 4, -1. So look, this was the vertex of the parent, this was the vertex of that one, that's the vertex of that one, and that's the vertex of that one. So the vertex just got shifted and transformed over to 2, 3. So we know the original function was a parabola, and that means this one's going to have the same shape. So it's just going to be another parabola. But my final parabola has been shifted right 2, flipped over the horizontal axis, and then shifted up 3. So if I were to graph the original is right here. This is the original parent function in red. But if I take that red parabola and I go right 2, flip it over the x-axis, and up 3, I get the blue one, which is what I wanted. So once you get the hang of this, you can look at functions like g here and say, oh, that's just a parabola that's been shifted right 2, flipped over the horizontal axis, and then shifted up 3. You can do that quickly and then plot those 5 points and graph it if you were doing this all on your own and not with an audience like me, where I need a little bit more from you to gauge your understanding. So for homework, I'm going to need to see this exact process here, where you write down the parent function and 5 points on it, and then each subsequent transformation in the correct order, t-chart for each one, and then graph it. And I'm only doing that so I can gauge your understanding. I need a glimpse into what's going on in your head. And if you make mistakes, I need to know why and where. Now, how do you know what order to do these in? Well, it's easier than you think. Once you have a grasp of the transformations, all you're really doing is adding or subtracting to x or y and multiplying times x or y. Well, we know from the order of operations way back in Algebra 1, you always should do any multiplication before you do any addition subtraction. So to get the order of the transformations correct, just do all the multiplication for x or y before you do any addition or subtraction for x or y. Just always multiply before you do any add or subtract for any given variable. Let's try another one. So I have f of x equals the principal square root of 4 minus 2x. Well, that looks an awful lot like this parent function. Y equals the principal square root of x. And that's a function we're familiar with. So let's do a quick t-chart. This is one of the ones that has a quote-unquote starting point because its domain's not all real numbers. And that starting point is 0. And then you can use a calculator if you want, but otherwise just pick some numbers you can do the arithmetic for quickly, like 1 and 4 and 9 and 16. Feel free to use a calculator and do decimals if you wish. There's nothing wrong with that. Now, notice we have x is being multiplied by 2 or negative 2 and then having 4 added to it. So it's got two things going on. It's got some sort of horizontal stretch and compress as well as a horizontal shift. So anytime you notice that there's a stretch compress with x and a horizontal shift, then to make your job easier, you're going to want to factor out the coefficient of x. So notice the coefficient of x is negative 2. I'm going to factor out a negative 2. I'm going to factor out a negative 2. And I know you're thinking, wait a minute. Now I've got the square root of a negative number. Well, not exactly. It depends on what x is. So depending on what x is, this will still work out to be a positive number. Because remember, the original domain wasn't all real numbers. So as we transform it, the domain is never going to be all real numbers. It's always going to be some sort of restricted domain rather than all real numbers. So we're okay. All right, so let's go through our transformations. Transformation 1, I've got x is replaced, well, let's see, we've got a negative 2 times x and a negative 1 times x. So those are horizontal stretch. That's a horizontal stretch or compression. It's also a flip over the y-axis. But I also have x minus 2, so it eventually is going to get shifted right 2. Well, to get the order correct, just make sure you do all the multiplication or division first, and then worry about any addition or subtraction. So, for example, you could have your next transformation be replace x with 2x. Replace x with 2x. Well, if we do that, it looks like you take x times 2, but as we discussed earlier, you actually divide by 2. So anytime x is replaced, you do the inverse arithmetic. So you're going to divide by 2. So divide by 2, divide by 2, divide by 2, divide by 2. You don't do anything to the y values. And then our next transformation, you're going to replace x with negative x. So notice that would be negative 2x, which is what I have up here. So another way to think of this, with a little bit of simplifying, would be that. You don't have to write it that way. But we're replacing x with negative x, so my new coordinates, you divide x by negative 1. We don't change y. And then my final transformation, to get the original graph f, I'm just going to replace x. So I'm going to take this x out and put x minus 2 in its place, which shifts it right 2. So we're just going to shift it to the right 2. So I'm going to end up at 2. If I did that right, 0 plus 2, and then a half plus 2, that'd be plus 2, plus 2, plus 2. I think we're okay. And then we're not going to touch the y's. So let's go plot those. So this was my end point. There's my end point, end point, end point. So there's the end point. The end point would going to be 2, 0. Then 1.5, 1. 0, 2. Negative 2.5, 3. Negative 6, 4. But remember, this is my endpoint, so it's going to extend this way. So it's still a square root, same shape as a square root, principal square root function. But remember, it got flipped over the y-axis, so it's headed to the left. It normally heads to the right, but this one's headed to the left because it got flipped over the y-axis. All right, sometimes, again, this isn't necessarily an application question, but just to have you play around with these transformations, we want to make sure we understand how you would describe them verbally as well as numerically. So to see if we can make that connection, we've got this example here. Write a function whose graph has the same shape as the cube root function. So that's our parent. That's the shape we want, but it's been shifted down 8. So the very first thing they say to do is go down 8. Order is not up to us here. We're being told what to do. So if you shift it down 8, then you would take the parent function and subtract 8 from all its y values. So down 8, did it. Reflect over the y-axis. Reflect over the y-axis. Well, if you want to go over the y-axis, you replace x with negative x. Done. So reflect over the y-axis, done. And then shift left 3/4. Left 3/4. So to go left 3/4, you replace x with x plus 3/4, because that shifts it left 3/4 units. So again, you have to go in the order that you're told. Order's not up to us here. So it said down 8, that was this one. Then it said flip it over the y-axis, that was this one. And then it said finally go left 3/4, that's this one. So this is the final result. That function right there has this shape, but it's been shifted down 8, flipped over the y-axis, and left 3/4 units. It didn't say to graph, so we don't need to graph it.